Hey, Year 11! Ah. How's it going? How's it going, everybody? Oh, I miss you guys. Yeah. It's hard not being in school. I much prefer it. It's nice to see you guys and to be chatting. Not being in school. Turning off my other laptop. Oh. Well, paper 2 today. Paper 2. Emmeline, can I ask a favor? Can thanks, Emmeline. Make it into a gift. Morning, Tom. It's good to see you. Emmeline, yeah, sorry, can you do me a favor? Can you write down the time when I get to each question, and then I'll post it onto the YouTube so people can click that bit in the timing thing and it takes them straight to the question. Oh, I'm pretty sure I'm going a little bit crazy. Cabin fever. Timestamps. Yes, timestamps. Yes. Oh, thank you so much, Emmeline. I really appreciate it. Actually, do you know what? I've got another request. Do you know, I've got like the YouTube video. I need a character. I need a character that's me, do you know, to be like a picture. Do you know, like a picture of a scientist like that? Okay, maybe not that one. It needs to have like spiky hair and big brown glasses and, you know, and I need like a caricature. I'm going to see if I can find you an example. Theme song. Obviously, I need a theme song. Chemistry. I definitely need to have a theme song. I'll work on that, Emmeline. I'll work on it. I'll have a go at writing my own theme song. But I need to have like an image that I can put up for like my webinars. And I'm wondering if you guys could help me doing it. That'd be amazing. You guys can design my YouTube logo. Chemistry. Yeah. I don't understand all of these. Chemistry with Mr. Duncan. Exactly. And then I need like a caricature, like a scientific caricature. That's what I'm thinking. Right. Well, I've got 4 of you here. Should we crack on with the video? Let's do share screen. Boom. There we go. And then click on that one. There we go. Hi, Arena. That's great to see you. I don't understand all of these crazy letters. I don't get it. I don't know whether it's some kind of code. Meryl. Okay. Right. Let's do that one. I can now get rid of all that stuff and go paper. Oh, no. I think it's all set up. Yeah, there we go. So I'll just take the keyboard off my laptop. There we go. Okay, so usual thing. We're looking at paper 2. We did paper 1 in those 2 pieces. I definitely need to go back and timestamp them. That would actually be really useful. But just confirming with all you guys that this is the one that you guys have had a go at. The next one's going to be 2016. I'm going to be doing an A-level webinar as well, by the way, of a paper 1 through if you want to come along and see the kind of questions you're going to get at A-level. More than welcome to attend. I'm doing a reactions of alkenes, actually, with year 12s at 2 o'clock today. I'm just finishing off a specification. So you're more than welcome to attend year 11s if you want. Okay, so question 1 started straight off at the periodic table. Just to quickly remind you guys, Edexcel and the periodic table for GCSE, this is the table you're actually going to get in your exam. This is the actual one. I went onto the Edexcel website. I went through your specification, went to the bottom, found the table, and I cut it out because I thought it'd be really useful just to flag a couple of people. Copper is 63.5, chlorine is 35.5, but all the rest of them are to whole numbers. So it's something to bear in mind. So the first question on the paper is simply an atom of an element has an atomic number of 6. So that's now telling us who it is. Yes, we've got, oh, so straight away it's carbon. Carbon is element number 6 and it has a mass number of 12. Oh, they're giving us the one straight out the periodic table, nothing special. Yeah, they've given us the bog standard one, the most common isotope, carbon-12. It's nice for me just to do a reminder for you guys of a definition at this point. Relative atomic mass. Yeah, atomic mass. It's a definition which I'd like to ask. It's one of the hardest definitions there is for GCSE chemistry. And this is the average mass. I haven't seen it in a while on a paper, so I'm kind of expecting it to appear soon. The average mass of an atom, and the average mass of an atom divided by 1/12 the mass of one atom of carbon-12. It's nice for me just to remind you guys of a definition that, as I said, very challenging. That's a level 7-8. That's a love 7-8, that is, because most students won't remember it correctly, and I haven't seen it in a while, so I'm kind of expecting it. Okay, so straight away, atomic number, of course, is the number of protons. So the number of protons is 6. The number of neutrons is the mass number minus the atomic number. So that's protons and neutrons. This is just protons, so minus the protons and you get 6. And the number of electrons, of course, because it's an atom, they are the number of protons matches the number of electrons. So 6, 6, and 6. I think that those numbers there would freak a student out because they're all the same. Yeah, it's quite unusual. They usually give you an odd isotope like carbon-13. But in this case, they're just looking to freak students out by giving them one where all the numbers are the same. Don't panic. You know what you're doing. Good, solid knowledge there will support you in that. Okay. How many electrons are there in the outer shell of X? Oh, that's easy. It's the group number. Yeah, remember that when we read the periodic table, yeah, the periods, these are the periods. This tells you the shell number. So X has 4 shells. Yeah, what you imagine is that the nucleus of the atom is there on the periodic table. And so you can read the shells off. Yeah, and that the group number tells us, I shouldn't really erase it, but the group number tells you the number of electrons in the outer energy level. I love the fact that they're allowed to use that word, but you're not. Just bear that in mind. So X has got 3 electrons in its outer energy level. There are 31 protons in an atom X. Using this information, explain how many protons there are in Z. Oh, well, the answer is 33. So you're going to get 1 mark for saying 33. And then you need to explain how you know this. And you know this because the modern periodic table moves across from left to right by an increase of protons by 1. Yeah. So that's what's happening. They're just, as we move from left to right across the table, the increase in proton number goes up by 1. So it's 33 due to table in order of atomic number I'm actually going to put full stop there. Yeah, atomic number tells us number of protons. I'm going the whole hog. I don't know what they want here. Number of protons, full stop. Atomic number increases by 1 as you move right across a period. Wow, it seems like an awfully long answer that for 2 marks, considering that there is going to be 1 mark, but I don't know what they're after. Yeah, do they want the fact that the table's in order? Do they want the fact that the atomic number tells us the proton number? Do they want the fact that it increases as we move across 1 every time? So I don't know. I'm going the whole hog. I'm very tempted to check a mark scheme at that point. Yeah, I'm going to do it. If there's any doubts in your mind, which I definitely have on that, I just want to see which bit they exactly wanted. There we go. 33. Z is 2 places, or Z is in group 5, X is in, ignore reference to atomic number increasing by 2, ignore number of protons increases with the group number, ignore reference to element being arranged according to number of protons. It's really funny. Yeah, except 2 more protons. That makes no sense. So Z is 2 places after. What a ridiculous answer. Due to the table being an order of atomic number left as a number of protons, atomic number increases by 1 as you move right across the period. Hey, Laura, lovely to see you. Oh, I miss my year 10s as well. I miss it all. I feel like I want to add that in. I don't like my answer. Yeah. Z is 2 places to right of X. Stupid people. What is the electronic configuration of Q? Where's Q? Hey, Q. There's Q. So, right, guys, I'm teaching you this methodology. You know, I've been teaching you guys this now for 2 years. I'm just reminding you that when you're asked to do electronic configurations, you need to make sure that you're running the process and not just... Lots of students learn this number. Lots of students learn 2882. That's what they learn. That's calcium. Lots of students learn that. Yeah, but you really shouldn't. The reason why, CA 20 and 40, by the way, but you really shouldn't do it that way. What you should be doing is reading the periodic table from left to right. So if you notice, in the first period, there are 2 elements. So that's 2 electrons. In the second row, there are 8, 2 and 6. So there's 8. And that's my finished product for Q, because I've just hit Q. Yeah? And you should be, if you go to calcium, which is here, you get another 8 and then 2. That's how you should be doing this particular question. Just try to be using, because there's method in my madness here, folks. I'm preparing you for A-level. Yeah, so this one's just 2,8. Argon, I believe. Argon the Stranger. Yeah, that's actually what argon comes from. State 1 similarity and 1 difference between the electronic configurations of J and T. Similarity and difference, J and T. Right. So there's J and T. So they both have 1 electron in their outer energy level. Perfect. Both have 1 electron. And I'm going to be good now today. I'm actually going to write... sorry. Pausing the stupid video. Both have 1 electron. I'm actually being good and rather than writing E minus, because you can't do that on your exam. Both have 1 electron in outer energy level. Notice I'm not using the term shell. Yeah, it's good practice. The difference is that J has 2 energy levels and T has 3. J has 2 energy levels, and T has 3 energy levels. 3 energy levels. Energy loves levels. There you go. I know I've run off the paper, but I'm writing too bit. Next, ethene is an unsaturated hydrocarbon. Just a reminder, definition of the word unsaturated, a compound that contains I'm just giving you all those extra questions because we know they're going to be there. A compound that contains a carbon-carbon double bond. Yeah, carbon. see what I've done there? Put carbon with a double dash, like yeah. Carbon-carbon double bond. Definition of hydrocarbon. A compound, you realize, by the way, there's a mark for the word compound. A compound made from only carbon and hydrogen. I'm going to shrink my pen. It's a bit fat. Carbon and hydrogen. Whoop, whoop. There we go. I like it. Right, give the molecular formula. So there's methane, ethane, ethene. Winner. Yeah, so there's ethene. And then there's, propene as well. It's clever. You should all be able to name all of those by now, folks. Ethene is bubbled into bromine water until there is no further change. What is the appearance of the solution formed? It is colorless. By the way, be warned, be careful. Yeah, that they've actually been super nice there. I was expecting to see the word clear, but they didn't. They've been really nice there and actually not include. That's the most common mistake at GCSE. Students get the word clear and colorless mixed up. They are not the same. Yeah, this means see-through. Yeah, this means no color. And bromine water is orange, but it's actually clear orange. Isn't that a funny thing to say? Clear orange, because you can see through it. Ethene can be formed from ethanol. What type of reaction is this? You're removing. That's really clever. Let's have a look. Let's have a look at what ethanol looks like. Our Friday night molecule. Whoop, whoop. There's ethanol. F, of course, being 2 carbons. F. And then we have an, because it's a single bond. And then this gives us our ol ending. Yeah, so there's ethanol. And we're going to turn that into ethene. Yeah, so we've got eth, 2 carbons. Yeah, ene, because it's a carbon-carbon double bond. And then there's no other group, just H's, so ethene. So what have we removed? We have removed that group there and him. Yeah, if you put those two together, then you get water. This is a dehydration. So we're going to go for a dehydration on that bad boy. I like it. Next. Okay. Oh, cracking. I love these diagrams. Got to watch for suck back. It's a major question that tends to come up in terms of this. Remove the tube before you stop heating, all that jazz. Give the name of this type of thermal decomposition. Cracking. This is cracking. This is a very special type of thermal decomp because we're cracking a hydrocarbon. So we're decomposing a hydrocarbon. It's a very special name for it because it's special, because we do it so much. Porous pot contains such as silica and alumina. Ooh, I keep seeing this at Excel. Zeolite is the actual name of this catalyst. Yeah, you're also allowed to call it alumina oxide, I believe, which is stupid. It's actually alumina silicate. I don't like any of it. Zeolite is the name I want you to learn. What is the purpose of this? It's a catalyst. Just to remind you, it's nice for me to mention the two. Remember that catalysts. Students struggle with that. I don't know. They do. They shouldn't, but they do. The reason being is there's two very distinct questions that students get wrong or get confused with, which is what is a catalyst? What is a cat? And how does a cat work? They are two very different questions. It's usually not a how, it's an explain. Yeah, explain what a cat does. Yeah, explain catalysts. What is a catalyst? Explain cat work. Nice, I'll do. Mr. Duncan, so if you mention alumina, we automatically assume it's zeolite. Yes. The catalyst is given a special name because there are actually a variety of them, Merrill. But zeolite is the name given to like the group of chemicals. And yeah, they're a type of alumina silicates. I just don't want, now that you've mentioned it, I'm just going to go to the mark scheme and check everything so far. 2.8, it's all good. They allow a dot or a comma, that's good to know. Do not accept 28, lol. Similarities, same number of electrons in outer shell. Do they allow energy level? They darn well should do. Well, they should in fact not be doing it. Except rings and energy levels in place of shells. Yes, damn right. Yours is the wrong answer, Edexcel. Sorry. Colorless, dehydration, cracking, catalyst. Right. There's of course no name for it. They just call it alumina here. But so Merrill, you're absolutely right. Yes. Just to quickly do these two questions. Yeah. What is a cat? A substance that increases the rate of reaction while itself not being used up. I know. A substance that increases rate of reaction. Yeah, I'm just gonna put react just because I've run out of ion. Rate of reaction, but itself not used up. They last forever. Next, how does it work? It provides an alternative route with a lower activation energy. Question number 3. Suggest why the gas collected in the mixture is not pure ethene. That's a great question. I have seen so many different varieties of this question. So just to explain, folks. So I think everyone here, when we did this practical in class, we talked about you don't collect the gas for the first 2-3 minutes. The reason being is you've got to get this hot. And what you're going to get here is, number 1, we had air in the system. I'm going to shrink my pen as far as possible. In the tube at the beginning of the experiment, there was air. So as soon as I heat this, the air expands. So the first thing that's going to go down this tube in the first 2 minutes is the air. We don't want the air, but they didn't do that. They've just heated it and collected the gas. So most of this in here is just going to be a mixture of, it's just air, it's oxygen and nitrogen mostly, yeah? But then what also is gonna happen is, then before the cracking starts, the liquid, the paraffin, the decane, yeah, the liquid oil, so this is oil liquid on here, is going to evaporate. So the oil's going to start evaporating, and the catalyst won't be hot to crack it. So I'm also going to get going down the tube. At a second point, I'm going to have vaporized oil. So I'm going to have oil that is not been cracked. I'm going to have decane, gaseous decane. Yeah. Then once this gets hot enough, once we get this point here to be glowing red hot, we then start to see the cracking process happen, and we then get ethene coming in third. So you don't collect the gas for the first 2-3 minutes. I think we were more focused on not blowing up the test tubes. Yes, Tom, we were. You're absolutely right. I have had so many nightmare practicals on that. I seem to recall that our practical was flawless. There wasn't a single death. That was amazing. Like, I was made up with that. I mean, I've killed several students with that practical before, and, you know, trying to get rid of bodies is a nightmare. I'm suddenly realizing that I'm live on YouTube. Probably the best thing that I'm probably not really meant to be saying that. But yeah, we had no deaths. Yeah, 6 out of 6 total success rate. It was amazing. Couldn't believe it. Suggest why the gas. Oh, by the way, I'm just going to write on how a cat works. Provides. Sorry, I can't do it. Provides alternative route. An alternative route of reaction. With a, if you miss those words, you lose it. You lose both. Wow, Meryl, you got something you want to confess. You realize that your friends are going to watch your criminal confession. Yeah, I realize that now. It's all right. I'll go back and edit it. Would it be a 0% success rate? Maybe. That might be a better way of looking at it. Reaction with a lower activation energy. Therefore, more particles have activation energy, therefore more successful collisions. Winner. Next, suggest why the gas collected is not pure ethene. Air from tube also collected. Also some vaporized decane. I'm going to want to check this, by the way. Decane. And we're also going to have vaporized octane as well. We're going to have a small amount of vaporized and vaporized octane, because the decane loses 2 to become ethene and octane. Also, side reactions. We don't know what we're going to crack. Okay, cracking produces 2 or more products. Other products are formed. Identify possible products, except molecules, except hydrogen. Ignore decane decomposes. Decane contains no reference to air. You liars. Yeah, other products are formed. Identify possible products. Not all decane composes. Water vapor present, not just water. Nice. So they're ignoring the air. That's so, I hate that. So irritating. Yeah. Yep. Anyway, so we still get it. Yeah, air from tube also collected, also some vaporized decane and some vaporized octane. So absolutely fine. I will definitely get that. By the way, I've got to watch out in these questions for when they say give one answer, and then it becomes a bit more tricky. I don't have to pick the one I want. But in this case, I can write down anything I like. I can write down all of them. So magnesium reacts with oxygen in air to form magnesium oxide. Okay. We need to actually, just to mention magnesium, folks, EdXL, I need to do a webinar on all of the practicals. I'm going to do that. I will, because that'd be super handy, that. EdXL loves magnesium. Mg is a really interesting metal. The reason being is it goes through a whole variety of reactions. Number one, it can burn in oxygen to form magnesium oxide, balance the equation. Yeah, that's the bright white one. That's where you see the ribbon, yeah, and you're holding it in a pair of tongs. There we go. Holding a pair of tongs and you see the bright white light. You also get another observation, just so you know. You get bright white light, bright white light. You also get smoke, white, and you have to say white smoke. Yeah, you get white smoke. And the reason why you're getting white smoke is because you're making magnesium oxide, which is an ionic solid. Even at these temperatures, it cools down, turns into a solid. So you're seeing the white smoke of magnesium oxide solid. And that reaction burns at over 2,600 degrees Celsius. That's crazy hot. Magnesium then also does some other things. It also reacts with water vapor as a gas, reacts with steam. Yeah. And this one's a practical that you definitely, hey Ira, good to see you. Reacts with steam to form magnesium oxide and hydrogen, which is really unusual. It's actually putting the water through thermal decomposition. That one, by the way, has a diagram that goes with it. That's the picture of a boiling tube like this. It's got the ribbon in the middle, cotton wool with water on it, and then they heat this, and then they heat this, and as the steam passes over it, you get the bright white light, and then there's a cork at the end of the boiling tube, like this. And you get the gas coming out here, and you can actually light it on fire, and you get a beautiful blue flame. Beautiful. They love this practical. You have reaction of magnesium and steam. Just thought I'd mention it. So it then says, the apparatus in the thing was used to investigate a decreased volume of gas when magnesium burns in air. Okay, never seen that before. It's going to suck. It's going to make it float. This is to test content of air. Wow, I've never seen them. I might try this. That would actually be, you're going to turn it into a, yeah, could totally do that. They also do this with phosphorus, by the way. Lots of practicals and demonstrations I need to work on. The stopper is removed and the magnesium is lit. The stopper is then quickly replaced. After the flame goes out, there is some magnesium left in the basin. What color of flame was produced when the magnesium? The answer is white. Yeah. What is the color of the solid produced with magnesium? Is white. Isn't that interesting? Lol. White and white. Oh, I need to check that answer immediately. That's vile. White and white. There you go. Right. Next. The volume of the air in the bell jar at the start of the experiment is 1 liter. Oh, they've been nice there. Calculate the volume of gas you would expect to remain in the jar at the end of the experiment. Assume all the air was used up. Wow. I told you this year 11 over and over. You have to know the percentages of gases in the air. 78% nitrogen, 21% oxygen, 0.04 carbon dioxide. So hang on a minute. We know that oxygen, O2 gas, represents 21% of the air. 21% of the air we breathe. They put in 1 liter. So what's 21%? So I do 1,000 divided by 100 to give me 1%, which is 10. And then I'm going to multiply that by 21. I know that some of you guys would prefer to just do it as a simpler fraction of 1,000 multiplied by 21 over 100. I think that gives you the same answer, does it not? 1,000 multiplied by fraction 21 fraction over 100. It gives you the same answer, doesn't it? 210. So that'll actually give you the percentage of oxygen used. Now, this is really tricky because everyone's going to get this backwards. Yeah? So just to quickly just write that down, I get 210 centimeters cubed of oxygen. Now, here's the clever bit. That is what is going to get used up. This is used by the magnesium. So which means I now need to run a second bit. 1,000 minus 210 gives me, I'm doing this on a calculator, I kid you not, 790 centimeters cubed left behind in the jar. We're done. Yeah, lots of students are going to be putting in the 210. Do watch out. Easy mistake. In another experiment, the mass of magnesium that burned was 0.12 grams. Calculate the maximum mass of magnesium oxide that could have been formed. Wow, have they given you the, yeah, they gave you the equation, folks. There's the equation. You've got to remember, this is now into reacting mass calculations. Laura, you can have a go at this now. Yeah, since we've just finished, well, we haven't quite finished it actually. I ought to do that on a webinar. I'll do that. I'll finish off calculations. But in an experiment, the mass of magnesium, so we've got Mg, we need an equation. Now the equation is already there, but I'm going to rewrite it because it makes it easier for my working. Right, so step 1, get to moles. I have 0.12 grams of magnesium. Step 1, get to moles. Find moles. Grams over rams. Number of moles is grams over rams. How much does magnesium weigh? Magnesium, we go to the periodic table that the GCSE people gave us, and it weighs 24. It's over there. Nope. It's over there. 24. So I'm going to divide that by 24, and I'm going to get 0.12 divided by 24. Laura, will you be doing a Year 10 webinar during the holiday? Laura, yes, I think I will. I miss you guys. I think it'd be really good for us to finish off calculations and get it all boxed off. So yes, I will. I'll send out an invite. I might even send it to the whole of Year 10 just to make it easier. Or I could post on the classroom maybe. So I've got 5 times 10 to the minus 3 moles of magnesium. Calculate the maximum mass of magnesium oxide. Guys, step 2, use the ratio. And you've got to write it down. The ratio is 2 to 2. There's a mark for that, folks. Just watch out. Yeah, there's a mark for it. So it's a 2 to 2, which means I've got 5 times 10 to the minus 10 moles of magnesium oxide. Step number 3, get out of moles. We're looking for mass. So we're just going to reorganize grams over rams. Number of moles times by rams gives me grams. How much does magnesium oxide weigh? Right, so magnesium is 24 plus oxygen, which is 16, equaling 40, I believe. So I'm going to multiply that by 40 times by 40, and I get 0.2 grams. And I'm done. Winner. We can actually work out the amount of oxygen if you like, just to prove that, but we won't. I'm tempted to do it for Lara's sake. The ratio, the full ratio for that equation is 2 to 1 to 2. So I would have got half those moles, 2.5 times 10 to the minus 3, half the number of moles of oxygen multiplied by 32, because everyone knows exponential minus 3. Everyone knows now the MR for oxygen because it's in a pair. And we get 0.08 grams. And guess what happens? Oh, it adds up, baby. Winner. Winner. Next, apparatus electrolysis. Yay. State how these ionic half equations show that equal volumes of the two gases should be collected. Right, so they're both, this one, so the top, the negative electrode is gaining electrons. Remember, if electrons go in, this is, remember, in, out in reactions, reactants, products. Going in is gain. Yeah, the way you remember that is the word gain has the word in it. Yeah, these ones are these are loss. Yeah, these are being lost. I'll put lost. Yeah, so it tells us oil rig. Oxidation is the loss, so this is ox. And this one is reduction is the gain. That one's red. There we go. It's nice to do that. But notice the electrons are the same, and therefore they both make 1 mole of gas. Both equations, the ratio is 1 to 1. Both equations produce 1 mole of gas. We're done. Yeah, ratio is 1 to 1. I want to see a mark scheme. I want to see exactly how they phrased it. So well done for that, Mr. Duncan. 79. Yeah, good job. Magnesium got to the moles. There's the moles mark. Ratio M2, multiplying it by 40. It's stupid, you see. They've got rid of the ratio mark. I hate that. Bad chemistry. Bad at Excel. Bad. Don't like it. Correct statement about the connection between number of electrons. Ooh, e.g., same number of electrons on the same. Ooh, is that mark 1? Look at that. Reference to the number of moles. Oh, or reference to the number of moles of molecules being equal on either side. Equal moles of gases have equal volumes. Yeah. Volumes are proportional to moles. Yeah, okay. There's loads of stuff you could have said there. And I actually agree with them. There's quite that's quite a lot of lovely chemistry in there. Suggest why the volume of chlorine collected is less than expected. Some of the chlorine, we know that gases are soluble, especially chlorine. It goes into swimming pools. Yeah, chlorine is soluble, so some dissolves in the water. So just to quickly mention, this question is usually followed up with, suggest how a student could prevent it. You could say that the gas is collected, well, you could use a gas syringe to collect it. Oh no, technically it's still going to dissolve. You can't do anything about that in that particular electrolysis. You have no choice. Yeah, very little you can do about that. In electrolysis of brine, some of it always dissolves. The sample of solution near the negative electrode is tested with phenolphthalein. The indicator explain why the phenolphthalein turns pink. Because it's forming an alkali solution, and it's in the equation, folks. Look, negative electrode is producing OH minus. Yeah, everyone here needs to remember that OH minus, that's alkali. So if it was universal indicator, it would have turned purple, but with phenolphthalein, it's going to turn pink. So you're going to say at the negative electrode, I'll be good. At the negative electrode, OH minus ions are produced. These ions are alkali. Yeah, fine, nice and easy. Don't even think I need to. I'm going to check it anyway. Alkali solution greater than 7 hydroxide ions. Fine, we're done. Solution is alkali. OH minus formed. Winner. Did I miss a mark? No. Yeah, you want to say it was alkali. The table shows 2 methods of testing for chlorine. Damp blue litmus paper. Observation. Ooh. Damp blue's litmus paper will turn red, then bleaches. Yeah, there we go. Turns red, then bleaches. Test for chlorine gas. Bubbling the solution through potassium iodide. Now that's very interesting. Right. So guys, potassium iodide, Ki, is a colorless solution. We all know this. Any group 1 metal compound is a white solid and colorless in solution. So I've got a solution containing Ki, and I'm going to bubble into that chlorine gas. Now, we know that in reality, what aqueous actually means, delete the side. What that little symbol there means is that in reality, this is our real picture. We have got potassium ions floating around and iodide ions floating around. That's what it actually means. Yes? Now, the potassium ion is never going to do anything. This is called a spectator ion. Now, pen's too fat. Just to say, loads of spectator ion. Now, just to mention, there are always students who go, hang on a minute, what do you mean by a spectator ion? So the first thing to do is explain the word spectator, which is somebody that watches. Yeah, a spectator literally means a watching ion. What that means is it ain't doing anything. Yeah, a spectator ion is an ion that is literally not doing anything. So if I actually just change that and go spectator ion does nothing. Yeah, it's just watching the reaction happen. That's why we call it a spectator. The reason why is because potassium is a very reactive group 1 metal. To try and give it back its electron, no. You'd need a metal more reactive than potassium. You need like rubidium or cesium. That's madness. Never going to happen. Or electrolysis. Electrolysis molten would do it. But then you're going to be making potassium metal at hundreds of degrees, which would just catch fire on contact with air. So you don't really want to be doing that either. But the iodide ion, on the other hand, the iodide ion has got an extra electron. And chlorine gets introduced to here. Now remember, chlorine is green. Yeah, they actually accept, Edexcel seem to accept yellow-green, but I don't like it. The answer's green. Chlorine's a green gas. And the chlorine's going to dissolve in the water. But the chlorine is more reactive. I'm going to make my pen fat again. The chlorine is more reactive than the iodine. What that means is the chlorine is going to take the electron from iodide. This is the iodide ion. Shouldn't have been calling it iodine. I do apologize. This is the iodide ion, and this is chlorine. It's an ene because it's in a pair. It's going to steal the electron and become chloride, and I'm going to turn iodide into iodine. I need to balance it. There we go. So this is called the ionic equation. Ionic equation. Yeah. In this case, for displacement is what's actually happening. But it's actually a redox. We've got the chlorine is oxidizing the iodide to iodine, and the iodide is reducing the chlorine to chloride. Holy moly, it's difficult, isn't it? I can go further into explaining why that happens, by the way. Yeah, it's because, I don't know what, I'm going to talk about the number of shells and how chlorine has fewer shells. Chlorine has 3 shells. Yeah, chlorine has 3. Iodine has 5. Iodine's enormous. And iodide, the extra electron, is miles from the nucleus. Of chlorine has 7 electrons in its outer shell. Of course it's going to take it. It's just going to rip that off. Yeah, it's the outer energy level is close to the nucleus. It's what makes it more reactive. Yeah, it's just nice to mention that. Really good chemistry going on there. Statewide, okay, so they're going to say what we're going to see happen. Right, so the observation is we're going to see iodine being made, and iodine in water is brown. Group 7 is one of the hardest topics, folks, at GCSE. It's one of the hardest. Solution turns brown. Really tough. It gets harder when you get to A-level as well, so knowing this at GCSE is really, really good because it's very supportive. We don't tend to reteach it. Statewide chlorine is sometimes added to water supplies. It kills bacteria. That one's easy. Yeah, that one's just flat out knowledge, folks. You can also say to sterilize if you like. I prefer kill bacteria. But sterilize is the same thing. Chlorine is used in the manufacturing of hydrogen chloride. Oh, HCl. I like it. Notice it's not an acid. It's a gas. Remember, that there is not acidic until it's in water. Acids cannot be acids unless they're in water. Yeah? Write a chemical equation to show the formation. Right, formation. Chemical equation, draw my arrow. To formation of HCl from hydrogen and chlorine and balance. And I'm done. Do I need state symbols? Yeah, can add them if I like. They're all gases. It's quite nice. They're all gases. Gas. You don't need the state symbols. They won't care. How is hydrogen chloride gas converted into hydrochloric acid? Add to water. How easy is that? Add to water. We're done. Whoop, whoop. Thank you. Question number 5. A teacher investigates the temperature changes that occur when sodium hydroxide is added to an acid. Okay, to hydrochloric acid. So this is calorimetry, folks. State two variables. So placed some acid. What? I'm going to highlight the ridiculous words. Some acid in a glass beaker and measured its temperature. Added a known volume of sodium hydroxide, stirred the mixture and recorded the highest temperature reached. Repeat the experiment with different volumes of sodium hydroxide. Some. So we're going to say volume of acid for 1. State 2 factors they need to keep constant and make sure that's a valid investigation. But we also need the same concentration of acid and sodium hydroxide. Yeah, whenever we get these acid and alkali ones, guys, concentration needs to set off in your mind. It's because it's always one that's going to be there. Same concentration of acid and sodium hydroxide. I like it. Next. Explain how the use of a polystyrene cup in place of the glass beaker will affect the accuracy. It will improve accuracy. We know this. Improve accuracy. And we're going to say why. Because it's going to reduce heat loss. Nice and easy. Reduce heat loss. Polystyrene, it's an insulator. Dead easy. Next. Oh, okay. So, start temperature. Do you notice Edexcel doing their very normal trick here, 11? Look, final, initial. What people do and easily lost 2 marks is that students go, oh, I'm going to read this off, which is 17.0 degrees Celsius. How many decimal places do they want? I'm assuming they just want 1. 3 sig fig, that's 3 sig fig. So the initial, see, then they go, oh yeah, 17, lob that there. No, be careful. Initial goes here, 17.0, and the end one is 35, 36, 37, 38, 39. Final temperature, 39.0. Temperature change is 39 minus 17. Yes, I'm doing it on a calculator. I know, 22.0 degrees C. State how the temperature change shows whether the reaction between sodium hydroxide is exothermic or endothermic. It is exothermic. Exothermic due to temperature increasing. There we go. Heat is being lost to the surroundings. Next, I actually want to mark that. I'm just going to check. Okay. Right. Test with damp litmus paper. Ignore red as intermediate color, except decolorizes, bleaches it. So, by the way, I hate that. Edexcel, don't listen. It turns red, then bleaches. Yeah. Next, turns brown solution. I like it. Even a black precipitator equivalent. Sterilize it. Dissolve it in water, add to water. I like it. Yeah, same volumes, concentration of acid, same concentration of alkali, same rate of stirring, same starting temperature, which is wrong, but I hate that. It's wrong. It's not correct. You're looking for the temperature change. It doesn't make any difference if you have a difference in the starting temperature. Stupid people. It's incorrect. Yeah. Correct reference to accuracy. Yeah, increases. Correct reference to insulation to reduce heat loss. Final, oh, they didn't need the decimal place. Exothermic temperature increased. I like it. Right. Explain the shape of the graph. 2 marks. Ooh, how fascinating. That's a really, really weird graph to see. Right. Explain the shape of the graph. Okay. Would everyone agree? 2 marks, 2 sections. Section 1, section 2. So I'm going to say the temp from volumes 0 to, it's not quite on that line, but I feel like they want it to be. It's like here. It's awkward as. 21.5. Okay. From volumes 0 to 21.5, the temperature increased due to more alkali reacting with the acid. From vol 21.5 to 40, the temperature decreases. And why does it decrease? Why all of a sudden would it stop going up? The reason being is the alkali's gone into excess, folks. Yeah, they're adding more sodium hydroxide and there's no more acid to react. From 20, the temperature decreases due to all acid having been used up. Mark scheme, please. Definitely. Any two from the correct statements. Correct statement about the first part of the graph identified positive gradient, positive temperature increases. There's mine. Yeah, correct statement about top of graph identified as where lines cross intersection is the peak. It's only two from, so I can still get a correct statement about the second part of the graph identified as a negative temperature decrease. Oh, that's it. Temperature decreases. Yeah, notes. No reaction occurring, no acid left. There we go. Yeah, reaction continuing or acid being neutralized, some acid still unreacted, heat being produced. Yeah. Oh, I didn't actually do the heat being produced thing. The temperature increases due to more alkali reacting with the acid. Okay, there you go. That's fine. Yeah. 2 marks. I'll give myself that. It's all right. Next, question number 6. Timestamp it for me. Emmeline, you're doing a fab job. Give the name of the gas produced. It's carbon monoxide. It's easy enough. Carbon monoxide. And it's toxic because it binds to your blood. CO binds to hemoglobin permanently. I don't know, my tablet just went mad. Permanently. So oxygen cannot be carried. You actually die from asphyxiation. It's actually a really good way to go, apparently. Very painless. You fall asleep. Apparently so. Anyway, phosphorus sulfide is one of the reactants used in match heads. Hi, Mr. Duncan. Hey, Shanley. It's so nice to see you. Oh, I miss you guys so much. Balance the equation. Ooh, that's exciting. 6 potassiums. 6 potassiums. 6 chlorines. 6 chlorines. Whoa. 6, 12, 18 oxygens. Oh, no. Okay, gonna skip oxygen. Gonna do sulfur first. Eek. Sulfur, phosphorus, 4 and 4. Right, I've got 1 sulfur here, but then, so total sulfurs on this side is 4, but only 1 over here. Right, let's do that. So sulfur now adds up. Does the oxygen? And the answer is it does. Magic. Guys, that's it. Wow. Seems awfully easy. Let's check. 6 potassiums. My laptop's gone off. Hang on. There we go. 6 potassiums. Hang on, I'm just going to do it. I'm going to zoom in here. 6 potassiums. 6 potassiums. 6 chlorines. 6 chlorines. Next. 1 sulfur. 3 sulfurs. 4 sulfurs in total. 4 sulfurs here. Next. Phosphorus. 4 phosphoruses. 4 phosphoruses. Oxygen is going to be the tricky one. Right, so I have got 6 times 3, which is 6, 12, 18. And on this side, I have got 8 and 10, got 18. So it all adds up. Fine. Next, what term is used to describe the energy required to start a reaction? It is called the activation energy. Activation. Activation energy. Activation. Oh, that's a great song. It's the Activation song, by the way. It was a big hit in the 70s. Suddenly realized how embarrassing that was. Complete the table, giving the colors physical state. Oh, bromine's a liquid. It's nice. Do you know there's only 2 liquids on my periodic table? Just to show you. 2 liquids on the periodic table, and that is mercury and bromine. The only 2 liquids. All the rest are solids or gases. All of these guys here are solids, and then you've got a couple of gases over here. That's about it, really, and then gases. But most of it is just solids, but 2 liquids, just 2. Gotta know them, they're useful. Iodine, color, gray solid. I want to see that. Is it going to be gray or black? Which one will they want on a mark scheme? Carbon monoxide decreases capacity of blood to carry oxygen, stops blood from carrying oxygen. Gain, whatever. Next, 6 and 4, done. Activation energy. Black. They wanted black. Allow gray. Amazing. Allow gray. Winner. It is gray. It's not actually black. It's dark gray. It's actually a silvery, shiny gray if you really want to know. So I'm going to show you that. Dot and cross. Ooh, I like it. Phosphorus in the middle. Bromine, bromine, and bromine. Make everybody add up to 8. In the gap, dot and cross. Yeah, dot and cross in the gap. Going to shrink my pen. Yeah, there you go. Dot and cross in the gap. Then make everyone add up to 8. Bromine, 8. Phosphorus, 8. Bromine, 8. Bromine, 8. And I'm done. Whoop, whoop. Winner. Next. Phosphorus tribromide reacts with water to form a mixture of 2 acids. Ooh, wow, that's clever, isn't it? Phosphorus P, gonna make my pen a bit fatter. Let's make it fat, shall we? Got phosphorus tribromide. I don't know how to say that in Yorkshire. Phosphorus tribromide plus water plus H2O goes to 2 acids, HBr, and H3PO3. Oh, that's phosphorus acid, not phosphoric. Isn't that interesting? That's not phosphoric acid, that's phosphorus acid. Right, add it up. 1 phosphorus, 1 phosphorus. 3 bromines, 3 bromines, or bromides, in fact. 2 H's, 6. I need 6. There's 3 H's here and 3 here. So I need 6 in total, so I need a 3 here. Right, 3 oxygens. I'm a winner. Winner! Whoop, whoop. Yeah! Boom! Winner. Chicken dinner. Is that going to be the end? No, don't be the end. There we go. Number 8. State why the reaction in stage 1 is described as a reduction. Nickel oxide is losing oxygen. We know that oxidation is the gain of oxygen, reduction is the loss of oxygen, and in stage 1, nickel oxide is losing oxygen. We're done. Next, suggest why a low temperature produces a higher yield of nickel carbonate. Oh, that's a really weird nickel. Ugh, look at that. That's disgusting. That's actually a nickel complex. But you don't need to know that. It's A2 chemistry, that. Explain why, suggest why. Oh, in stage 2. It's an equilibrium, folks. So a low temperature is going to be favoring the forward reactions, exo. Yeah, that's hard, that, folks. Year 11, there's your you guys got that correct. That's the first really difficult understanding chemistry question on this paper. The forward reaction is exothermic. So lower temperature. What am I doing? Temperature, what? Lower temperature will shift equilibrium will shift the equilibrium to the, have I broken my pen already? No. Equilibrium to the right. Shift. Equilibrium, shouldn't say to the. Equilibrium from left to right. Greater yield. Hard question, folks. Love 8. Yeah, that's a love 8-9. First one, and it's an equilibrium one. Next, draw a labeled diagram of the particles of nickel. Right, nickel's a transition metal. It's going to be +2. How many do I need? Do you remember yesterday I made the embarrassing thing that Emmeline was like, Mr. Duncan, it says that there are 4 particles needed in the diagram, and I didn't read it. I'm just checking for that now. Nickel has a melting point of 1,455. Good conductor. Draw a particle arrangement of particles in nickel. I'm going to draw 6. Right, now this is metallic bonding here. Lara, you've also done this. Yeah, actually, I'm going to put, I don't like that. I'm going to put nickel 2+. That there is A level. You must include the symbol. Can't cheat. It's just good practice, to be fair. But at GCSE, they tend to just ignore. They just want the charge. But we'll see. Nickel 2+. Now I need 6. There's 2 electrons off each. So I need to do 1, 2, 3, 4, 5, 6 dots. There we go. And the dots represent electrons. Just going to do that. There we go. We're done. Explain in terms as to why nickel is malleable and is a good conductor of electricity. I'm so glad you found it funny, Emmeline. But do you know what? It's great for me to do this. That's why I don't look at the marking beforehand, because I benefit it just as from doing it just as much as you guys do. That's why I like doing it with you. I'm also a chemistry nerd. Right, 2 questions here, folks. Structure why it is malleable. So I'm going to say nickel is malleable due to atoms form organized layers, and those layers can slide. Slidey. Done. 2 marks. Boom. Now I need to explain why it's a good conductor of electricity. Nickel has a delocalized sea of electrons. Electrons that can flow. They need this. Excel love this. That can flow through the structure. Carrying charge. Through the structure. Carrying charge. So, good conductor. There we go. We're up. I've opened that by accident. Didn't mean to. Let's close that off. Nope. There we go. Next. I'm going to mark this now at this point. So, dot and cross. Nailed it. Balancing. Nailed it. Nickel has lost oxygen. I like it. Equilibrium position shifts to the right. Forward reaction is exothermic. Love it. Diagram showing minimum of 5 circles in rows. 2+ charge or 1+ charge is allowed. Some indication of electrons being between ions. Appropriate key. I like it. It'll do just fine. I like it. Malleability. They form layers, and those layers can slide. Delocalized electrons. That can flow, except move, mobile. Except sea of electrons. Ignore free electrons. Ooh, interesting. Ignore reference to intimately else because there isn't any. Flow when potential difference is applied. So I just need to say that they flow. Winner. I'll take it. No. Oh, I'm sad. The lesson is over. Oh, I always like hanging out with you guys. I'll bring it all back. Bring it back. Sing it back. There we go. Way! Hey guys! Right, oh, I am roasting. Right, guys, it has been an absolute pleasure to hang out with you guys, as always. Thank you so much for coming. Yes, I know I'm all sweaty. I love the fact that, yeah, Emily just laughs at me. I know, I'm sad. I miss you guys. Meryl, Lara, everyone, you are so welcome. I love doing these webinars. You know I do. I wouldn't do it if I didn't love doing them and seeing you guys and hanging out. Lara, I will send out an email regarding the I'm going to do a calculations webinar for year 10. We'll box off calculations. Say hi to Mr. Oh, Mel says hi, Miss Donna. Emmeline, you're more than welcome. Guys, stay safe. Look after yourselves. No worries, Tom. It's great to see you. Thank you for coming. Keep working hard, guys. It's so good to see you. Have a nice rest of your day. See you later. Give like a big stop.